Hello everyone, my name is Gharib and I'm an applied scientist at TripleBlind. TripleBlind is a startup that offers digital privacy as a service. In this video, I will be talking about one of our services called Blind Learning, which is an efficient, privacy-preserving approach for distributed learning. It is worth mentioning here that blind learning is actually a set of protocols and algorithms that enable advanced data analysis and training of machine learning models on distributed datasets. However, in this video, I'll use the term blind learning to explicitly refer to our distributed learning protocol for neural networks, which is built on top of split learning. Before I explain the protocol, however, let us take a quick look at the motivation for this work by identifying the privacy pain points in a typical machine learning lifecycle. Given a well-defined problem that requires a machine learning solution, the data scientists often starts by collecting, processing, and analyzing proper data to be consumed by some machine learning algorithm. It is well known that in order to build a robust machine learning model, specifically deep learning models, it is very important to use large amounts of data to build a powerful, robust, and fair models. However, data sharing among data owners is extremely difficult because of privacy regulations, data localization, and competition. Once we have proper data, we start training the machine learning model. And because machine learning models are programs or functions that generalize from data, they could actually leak data during the distributed training process. In addition, the privacy of the model itself could also be compromised. And finally, when we have a good model, the model is deployed and ready for inference. And at this stage, it is susceptible to several privacy concerns, including indirect data leakage, the user data that is used in the inference process, and the model privacy or its intellectual property. To address most of these challenges, specifically data sharing, several distributed learning paradigms have been proposed, and one of the most popular approaches is federated learning. And in the most straightforward setup, the protocol is orchestrated by a central server that manages the client's trainings and maintains a master copy called the global model. Generally speaking, the global model is generated at the server and it makes it available to all remote clients. Each one of the remote clients train the local copy of the model for a certain number of epochs and then share the updates with the server. The server aggregates those updates in some form, such as averaging these models, and then creates the global model, and this concludes one global training ground. The main advantage of federated learning is that it sends the model to the data, and therefore the data never leaves the data owner premises. Some of the main challenges of federated learning include direct data leakage, the model privacy is compromised, and the protocol requires large network bandwidth. In addition, it requires expensive computational resources at the client side. To address most of the challenges of federated learning, a new innovative technique called split learning was invented at MIT. Basically, split learning enables distributed learning by partitioning the neural network into consecutive chunks of layers among various parties. In its simplest form, each one of the clients has an identical part of the network, while the server has the other part of the network. Each one of the clients does a forward propagation up to the cut or the split layer and then sends the output of this layer, which is also referred to as smashed data, to the server, which then continues the forward propagation using the smashed data as an input. The server then calculates the loss function, does a backward propagation, and sends the gradients of the smashed data back to the client. And in the first standard approach of split learning, this process is done in a sequential round-robin fashion, one client at a time. And the main advantages of split learning is that the training data never leaves the premises of the data owner. Another very important advantage is that split learning enhances the privacy of the model itself, since unlike federated learning that shares the entire model with all clients, in split learning we only share one part of the model with the rest of the clients. Split learning also reduces the computational burdens on the clients because the clients train only part of the neural network. Another advantage is that split learning reduces the network bandwidth because it only exchanges a single layer of outputs with a server. And finally, and most importantly, it is also safe to assume that the models produced using split learning will always converge to the same level of models trained using the standard centralized procedure. However, some of the main challenges of split learning still include direct data leakage, and that split learning is slow to train due to the sequential round-based training. To this end, we present our distributed learning protocol called blind learning. The protocol is built on top of split learning and extends its functionality to overcome the challenges of split learning, specifically the data leakage and sequential training. In blind learning, each client receives an identical share of the model and all train in parallel. Smashed data is then sent to the server to complete the forward propagation process. The loss value is calculated for each client and then aggregated at the server's network using some different mechanisms based on the underlying approach and the nature of the datasets. Then the server starts the backward propagation and sends the gradients to each one of the clients to update their local shares of the model. The main goals of our blind learning is to enhance the privacy of the data, and in this case, the data never leaves the premises of the client, enhances the privacy of the model because again, we are only sharing parts of the model with the clients, and on top of that, we are reducing the direct data leakage that is caused by exchanging the smashed data with the server. So the main characteristics of blind learning is that it trains clients in parallel, it uses some averaging techniques to aggregate the server's results, and it also uses advanced techniques to aggregate the client's results. And then it uses distance correlation measurements to reduce the direct data leakage during training. Let's take a look at one of our aggregation methods at the server side. And this algorithm depends on using an averaged loss value from all clients to carry out a single back propagation process at the server side, and then shares the gradients with all the clients. This approach is suitable and efficient for the case of IID datasets. And what we see here is the general formula for the loss function when including the distance correlation measurement, whose main goal is to reduce the direct data leakage during training. What we see on the right is the actual utility loss function, such as the cross entropy loss. And what we see here on the left is a specialized data correlation metric that aims to reduce the correlation between the input data and the activations of the split layer. In other words, we want to optimize the values of the split layer outputs or the smash data in such a way that this smash data can be used to carry out a meaningful forward propagation at the server side, but those same activations or smash data should not be useful to reconstruct the raw data. Alright, I'm very excited now to show a quick demo of blind learning protocol in action using the TripleBlind's platform. I'll use the Fashion MNES dataset for the demo purposes. However, we assume that I do not have access to such a dataset and it is not freely available online. So first, I'll have to find this dataset and then use TripleBlind to enable distributed, privacy-preserving training using that dataset. The first thing I'm going to do is to visit the main TripleBlind application webpage where I can actually use the Datasets Explorer to find datasets of interest. And in this example, I'm going to look for the Fashion MNES dataset. I see there's one available here, and the data owner of this dataset have left some very useful information, such as the number of records, the labels, and the size of these images. There's also the price, the agreements, and a rich view of the characteristics of dataset. However, to be able to point towards this dataset that I would like to use it in my code, I can simply copy the ID of the dataset and come to my actual working environment. So here I am using Jupyter Notebook. I have already installed the TripleBlind's SDK that will allow me to run the blind learning protocol. To start the blind learning protocol is very easy. I'm going to import the required or the necessary libraries, specifically the TripleBlind one. I'm going to create a pointer towards the data set of interest by pasting its ID over here. I'm going to run the cell, and I see that we have successfully pointed towards that dataset, but still we do not have access to it. Before accessing the dataset, I'm going to create a data processor that's going to do some manipulation or transformations on the data, such as resizing it, defining the color of the images, and whether the channels are first or last, and the data type. I'm going to run the cell. And here's the fun part where we are going to build our neural network using the TripleBlind SDK API for the network builder. And everything is very similar to what you are familiar to in Keras or TensorFlow when building sequential models. The only thing different here is that we have a specific type of layers called the split layer. And the split layer defines where to split the actual model. And let's run this. And this is another fun part where we actually define all the parameters for the training job. So the loss function, the optimizer, the number of epochs, the test size of the dataset, and so on and so forth. I'm also going to run this. And here's the actual training. I'm going to create a training job and define the parameters and the dataset I would like to use and run this cell. You will notice that the training is right now waiting on something. And of course, it is waiting on the approval of the dataset owner for me to be able to use their dataset. So now I'm going to play the role of the dataset owner, and I'm going to enter the TripleBlind application. I see that there's an access request to use my Fashion MNIST dataset. I can approve it, or I can actually contact the data scientist that wishes to use this dataset to make a better agreement. But for this example, I'm just going to approve this job. If I go back to my notebook, I see that the training has already started, and we defined 2 epochs, so right now we are in epoch 1 of 2. And we see that the first epoch is done, and the accuracy is about 82% on 3000 images. Once the training is done, I'm the model owner. I can download the model, or I could expose it as well at TripleBlind for others to use. We also provide secure protocols for inferences, including secure multi-party computations. So this concludes our video for the blind learning protocol for neural networks. And here I would like to acknowledge our team members. I'd like also to acknowledge the interns of TripleBlind, specifically Praneeth Vepakomma from MIT, who made significant contributions to the distance correlation for reducing the direct data leakage from the split layer. We also thank Caitlin Storm from Johns Hopkins University and Sharon McCart from Purdue University. Thank you very much for watching. If you have any questions, please reach out and visit our website at TripleBlind.ai.